All right, let's get started. What happened to everybody? It's kind of empty in here. All right, so we have some stuff due tomorrow, right? We have our homework 1 and homework 3 due tomorrow in here. Exams are almost wrapped up. So what's going to happen tomorrow is one of two things, and it's yet to fully be decided. We will be having an on-campus interview tomorrow for the open lecturer position. And their schedule is a little bit tight, and that may mean that they need to teach in this class instead of 211 in the afternoon. If that is the case, then we will go over the exam on Monday. Otherwise, we should be able to go over it tomorrow. But basically, I offered up this class as that makes way more sense for their schedule than trying to teach because they need to fly out at 4, which means they need to be in line for TSA at like 2:30, and they want to tour the Chidi campus before they leave. It's a logistical nightmare. But basically, from your perspective, just know that there may be a guest lecturer here tomorrow, but if not, then the plan is to go over the exam. Questions on anything that's happening in this class ahead of going over the content?
So if this lecture is tomorrow, we're going to do the work, it's not.
We would have class, but the class would be their 211 lecture rather than our usual 300 lecture, which would be fine. We're just about a day ahead of my original plan. So I think that puts us on an adequate path. I don't think it gets in the way of our 8 timeline or anything else. I did reveal or create a new assignment yesterday that will be due next Wednesday. I try to keep that fairly easy and straightforward. And then also percent 8 related. So if you implement material from that assignment, that will help you study recursion for the 8. So I think that it doesn't get in the way of your 8 preparation and it helps your 8 preparation. Those were my design goals for the assignment for next week. Just making sure it was useful and relevant to what else is going on next week.
Remember, instead of the test grades posted already?
They are not. They're still being 100% finished up. They should be finished up probably this hour or next hour. TA is just finishing up the last few right now. But I don't know if the grades will be posted before we report them or not. But they look adequate from what I have seen. They're not it's not the best exam I've ever given, but it's not the worst exam I've ever given. Not on the extreme. Maybe. I would probably think that's okay if you're very curious and he's finished everybody's, just because that way there's no going once he's sure of the entire final process. But that's probably fine. I tend to offer that whenever I'm the one grading it. All right, last time we went over and had you focusing and working on Towers of Hanoi. So we are going to go over a solution to that. Did anybody manage to get it working? Maybe? I want to go over the recursive solution because it is really nice. It's actually really pleasant to work with. So we are going to do that. So Hanoi is not going to return anything. It's going to be doing all of the printing within the method. So it's going to be void. What does Hanoi need to take in order to work?
Number of discs.
We need to know the current number of disks. We're going to call that N. And we said that we had these 3 towers that we labeled A, B, and C. So we're going to pass these in as primitive characters. So how do I want to say from, let's say. From rod. And then we will pass in to rod, and we will pass in helper rod. And these will be the three characters of the towers that we are going to be using for this. Great. How are we actually going to go about this? So let's figure out the base case. Let's derive the base case. So we have some n. We need to move everything that's on top of that to the helper stack. We need to move the disk that is the nth disk over to the 2 rod, and then we need to move the remainder from the helper rod to the 2 rod. In the base case, there's only one disk, which means that there's nothing above it that needs to be moved. So in the base case, we just need to move we need to move disk 1 from rod to rod to rod. That's all we need to do. Wherever that happens to be is the destination for the current stack. So for this case, it will be the 3rd one over, but sometimes we're going to be wanting to move the nth rod there, which means the 2 rod for the stack above that is going to be the helper rod. So we'll see that as we go. So we want to say if n is 1, we're in our base case, then we want to print so how are we going to do this? Let's print take disk 1 from rod, and now we have some kind of variable here that we're going to say from rod. And then we are going to concatenate that to 2 rod. And I think that will tell us take disk 1 from rod A to rod C. As long as that is what's passed in as the original from rod and to rod. So I think that is the style that we want to print here. Once we're done with this, we're done with the whole thing, so we can just return. All right, that's the base case. Now imagine that we have n equals 2. That's probably the next easiest thing to imagine. So we're going to break this down into disk 2 and disk everything above 2, which is just 1. So in general, we want to move the 1 to the helper rod, the 2 to the 2 rod, and then the 1 to the 2 rod, right? That's how we want to do that. So the first one is going to be, since we don't know it's only a single rod, we need to recursively call this on n-1. So we're going to just say, we're going to call that tower, I didn't call it tower, I called it Hanoi. We're going to pass Hanoi. The new n is the current n-1. And I'm just going to leave that like that. n-1, the from rod, where we're moving it from stays the same, right? That the current from rod is where the 1 is going to be. So the from rod should stay the same. What is the 2 rod? Where are we moving that 1 to? Is it the same 2 rod as the 2 that we're trying to move, or is it the helper rod? Let's actually draw this out. I think it'd be easier to visualize this than trying to completely internalize it in our head. So we have this situation going on right now. And this is our from rod, this is our current 2 rod, and this is our current helper rod. This is where we want to move the entire stack. So to do this, it's going to be a 3-step process. Step 1 is moving that there. Step 2 is moving this here. And step 3 is moving this here. Does that make sense? So moving the from rod, we want one to end up at the helper rod. So the to rod for this subproblem of Hanoi is the helper rod. That's the destination of where we want this first rod, the first disk to end up. So the to rod is the helper, the current helper rod. And then the helper rod for this that is not going to be used at all is the to rod. But it would be used if n was greater than 2. So we need to consider it. So we solve that subproblem. That moves that stack to the helper rod. We then want to move this singular disk from the from rod to the to rod. That's not its own separate subproblem, that's just a single move. So we can straight up print it out. We're just gonna say take disk, but now we don't know which disk it is. Which disk is it? What number disk are we moving from the from rod to the to rod? This would be to the to rod. Yeah, in this case, it's the second disk, but in general, remember that this is trying to solve Hanoi of n. So if this is Hanoi of 5, then this is going to be disk 5. If this is Hanoi of 12, then this is going to be disk 12. So we actually want to use n here to tell us which disk we're actually moving to the destination. So take disk n from rod to rod, and now we're the destination is also the to rod, because we want to get it to its destination. Once we do that, we need to move the stack that's currently at the helper rod to the to rod. So we have one more call to Hanoi. As we don't know this is a single disk, this could be a stack of disks. So we want to move the stack of disks, which is of size n-1. The from rod is no longer the current from rod, it's the current helper rod. So we're going to move from the helper rod to the to rod using the from rod as the helper rod. Does that make sense? This is just saying we have a stack of stuff here. We want to move it here. So the helper rod, if this is the from rod, this is the to rod, is going to be this rod. That's going to be the one that the other ones go to. All right, what's next? Yeah, we're done. This solves the entire Hanoi problem. We just have to test it. As wild as that seems, this is the entirety of the solution. Let's write a main and verify that it works. Let's see, let's start and just verify that this works in the base case. We'll set n equals 1, and then we're going to call Hanoi on 1, I guess n, so that we can have this consistent. And then we're going to pass it the character A, the character B, and the character C. We run this, And we get take disk 1 from rod A to rod B. Because, oh, the 2 rod was next, this should be flipped. C and B, we have the 2 rod there, so from rod A to rod C is what we should be seeing, there we go. Now let's see if it solves Hanoi of 2 correctly. Disk 1 from A to B, disk 2 from A to C, disk 1, B to C. That solves Hanoi of 2. Is it going to work for 3? Someone verify this for me. Draw this out and see if this works. Yeah, it should take exactly 7 moves if it's right. So we have the right number of moves. 1, 2, 3, 4, 5, 6. Yeah, that is right. Not that I'm horribly surprised by that, but that's good. Hanoi of 8, that was that really difficult problem that we saw. Run it. And here is a solution for Hanoi of 8. The actual sequence of steps that you would need to run in order to solve Hanoi of 8. It's amazing to think that all of that work is done by just this few lines of code. So the way you think of this, if you're trying to generate it, is that you don't try to solve the entire problem. You just try to solve, you just assume that the subproblem is solved. All you have to do is, this is very similar to the math proof type of induction. Yeah, that's exactly right. Where you solve the base case, and basically you have, given that you've solved n minus 1, you solve n. For anyone who has seen induction before, this works exactly like that. That's all you need to solve a problem of arbitrary size. Given that we've solved a problem of size 1, which is the base case, we can solve a problem of size 2. Given that we can solve a problem of size 2, we can solve a problem of size 3. Given that we've solved a problem of size 3, we can solve a problem of size 4. And that continues forever. We just say, given that we can solve n minus 1, we can solve n. So Hanoi has 2 cases, the base case and a recursive case that says, given that we've solved it for size n minus 1, we can solve it for size n. And then we can pass in any value of n, and this just recursively works. So for those of you who are taking or have taken discrete, tie it to induction. If you have not yet taken discrete, when you see induction for the first time, it looks like a giant mess of math, and it's very confusing. Tie it to recursive thinking, and it will help it make so much more sense to you. All right, I think that solves Hanoi. I did though promise that I would show you what it looks like if you were to write this in an iterative fashion. Here we go. Here's the length of the iterative solution for towers of Hanoi. It's just a little bit longer. It uses something that we're going to start talking about right now, which is why I introduced it, the stack. We don't even need a stack if we solve it recursively. You don't need to understand that data structure. You don't need to understand how it works. You just solve it recursively. But here is an example of what it looks like iteratively. It's a little bit gross. You need lots of cases. If rod 2 is empty, if rod 1 is empty, if the first disk is bigger than the second disk, if the first disk is smaller than the second disk, you need all sorts of logic. With recursion, you don't need it at all. questions on our implementation, questions on why we care about recursion and how it can make your life just a little bit easier for certain kinds of problems that can be phrased in an inductive way. All right, let's talk stacks. So that's all I'm planning to cover with regards to recursion. I am hoping that with the little bit of extra practice that you have on your homework, that solidifies. But as always, with most computer science topics, I exist to introduce you to the topic. That does not necessarily mean that you are a master at it immediately afterwards. So find some additional practice problems on an as-needed basis. I can help you to identify those or find them in office hours and get some extra practice if you feel like you could use it. Kind of tough. All right, we're actually going to move on to our next an actual data structure. We've really only talked about lists so far. So this is the next kind of structure that is not a list. So one, it's great that lists exist. But it would be nice if we could improve on the list's weaknesses. Some of the operations of a list were big O of n, they were linear time. It would be nice if we had a structure that could do all of this in constant time. But to do this, we have to make some trade-offs. We have to make some restrictions to the kinds of problems that it can solve. So we want constant time get and remove. And you can't get constant time get and remove with any kind of list. You have to sacrifice one or the other. If you use an array list, you don't have constant time remove. If you use a linked list, you don't have constant time get. So just thinking outside of the box a little bit, what restrictions would we need to place on what a list can do if we wanted to guarantee this constant time get and remove? Something like that. We don't necessarily, the restriction is going to come in what elements we have access to. Yeah, that's exactly right. So instead of being able to get or remove any element of the collection, we're going to isolate and say we only have access to the last thing that we put in there. Not anything in the middle, not anything at the beginning, just the last thing we put in there. And that's not going to solve every problem in existence, but for the problems that it can solve, we end up with constant time everything. So it becomes very necessary as computer scientists to recognize when we have a problem that can be solved with such a structure because we can make it faster. So think in the back of your mind about what kinds of problems you would be able to solve if you only had access to the last element that you put into the collection. And we'll go over some of those as we continue talking, but keep that in the back of your mind. So it's an abstract data type because we're not going to specify how exactly this is implemented. And in fact, you can use a stack with any underlying list type. So you can have a stack that uses an underlying array list. You can have a stack that uses an underlying linked list. So because of that, it is an abstract data type. We don't specify what the underlying data type is. So we can't add in the middle of a stack. We can't remove from the middle. We can't access any element in the middle. We don't know what's there. We straight up can't even look at it. The visual example I have for people is thinking about something like a stack of plates. Let's say you're emptying a dishwasher and there's a clean plate in the dishwasher. And in the cabinet, there's an existing stack of plates. You don't want to waste any time. You want to do this as quickly as possible. Where do you put the clean plate? On the top. You don't try to put it in the middle of the stack of plates. You don't try to pick up the stack of plates and try to put it underneath the stack of plates. If you're worried about efficiency, you put it right on top and you're done. You don't need to manipulate the stack at all in order to just put it on top. All right, now you're really hungry. You want to put the food that you just made on a plate. You go to the cupboard. Which plate do you want to go grab? The top one. You don't want to grab one out of the middle. You don't want to grab the bottom one. All of that is way more work than just grabbing the top one. So we call this a last in, first out structure, or a LIFO. And my terrible joke is that in a room full of stacks and the next data type we will talk about queues, the stacks are the LIFO of the party. I got at least one face palm. I'm now happy. I can go to sleep happy tonight. So thinking about a stack object like a stack of plates helps a lot, and just visualizing where things go, what you have access to, but then you're kind of gonna flip the stack of plates on its side if you think of it as a list. And then you're always pulling off one side of the list and putting things on the other side of the list if you're thinking of the list horizontally. But we often draw stacks vertically, so it works like a stack of plates. So just take an array list that you're used to or a linked list and just think of drawing them now from the bottom up instead of horizontally. And you'll have the visualization for a stack. So underlying structure, can we implement it with an array list? Yes. Could we implement it with a linked list? Yes. There's nothing that specifies what we need here. Each one of these lists supports adding at the end, removing from the end. So we can just take a list and make that a field of the stack class. And then we will just restrict what of the underlying list's operations you can call. So we make the list a field of the stack object. And we're only going to implement public methods that interact with those list methods in ways that are efficient, that have constant time access. And we will straight up not allow access to the underlying list methods that have linear time. So yes, the list knows how to add in the middle, but the stack object that's interacting with that list is going to say, I can't do that. So it's just like a list with additional restrictions. So what do we need to store? What are the fields of the stack class on top of the underlying list? So we know we have the underlying list. What else do we need access to? Maybe the top of the stack? We need to know where to go to look for it. Yeah, so we need the size. The size of the stack tells us where to go find that last element. If the size of the stack is 6, what is the index in the list of the last element? Yeah, it's just one less than the size. So you do the list of size minus 1, and that grabs you the top of the stack. So let's take a look at what a stack can actually do. What is the associated behavior that we need to implement with a stack? That's it. We just need the 2 fields. We just need the list and we need the size. Nothing else needs to be stored. Push is what we call adding to a stack. So this is going to take an element that we pass into the method and it is going to add it to the top of the stack, which is just going to be a call to the list's add method, add at the end method. Remember that we cannot call the add in the middle method. Removing from a stack is called a pop. It returns that element and removes it from the list. We can also look at the top element of the stack without removing it from the stack. We call that a peek. So pop and peak look very, very similar, except that pop removes the element from the stack and thus from the underlying list. Peak does not. Both would return the same value. We need to be able to figure out the size. So the field that is the size is going to be private. We don't want people modifying that from the outside. Does that make sense? If as a user of a stack, I can just set the size of the stack to 20, that's gonna mess with the underlying code. So we want the size to be read-only, which means we need to write a getter for the size, but not a setter for the size. So this is just the size getter that allows us to read from the field from the outside, maintaining encapsulation. We also have a Boolean is empty that just tells us whether the size is 0. So my challenge for you for the rest of the class in groups, go ahead and write a static class that uses an underlying array list. Don't worry about making it work with a linked list. That's going to be part of your homework. But use an underlying array list and see if you can implement each of these methods.
Part of this.
No, the one that's going to be after that. Because this isn't going to be on the 8th, so I'm not going to assign anything that's not implemented until after the 8th. So if you're thinking about how to do this, take each one of these methods and think about what needs to change about the underlying list. What list methods do I call to do this? Don't directly access the list and try to find the exact element necessarily, but call like the list's .get method. The lists use the built-in list features here rather than trying to reinvent the wheel. Everybody know how to get started? Everybody being okay getting going? If you are not currently working with someone, I highly recommend it. Put your heads together. Have any questions I can answer?
Something we have to write these methods.
Yeah, I need to implement these methods, and doing this to the stack will involve doing something to this list. Make sure not to forget the constructor.
Sure, just,
You just submit it to the homework 3 rather than homework 1. Make sure you submit to both places, but yeah, we'll just write a driver for the functionality that we're testing, or use your driver.
we say, make sure this is the place.
If you're redoing homework 1, yeah. Probably start implementing it tomorrow. We'll give people the rest of class to finish it off. Get it working? Yeah. Nice. How are other people doing? How's progress? Getting there? Yeah. Yeah, within these, so you're not gonna define them.
Instantiate the array list like as the object.
Yeah, so in the constructor of the stack, you're going to say, so you're gonna define this as a field that does not get instantiated, and then in your constructor, so you would have like. We say. Yeah. I guess we should also have a T on it, stack T. And with a new array list comes an empty array list, which is exactly what we want. An empty stack should be made up of an empty array list. And then just make sure that the size is also 0. That's your constructor. Probably just have to you imported the list. Oh, yeah, I don't want to say this. You want to say, what is the name of your list docket? Here's what it means. Oh, yeah. What if you highlight a word again, what does it say? Oh, it says parentheses, not square brackets. Yeah, there you go.
I was like, what is that word?
Yeah. You can do that in C++, you can overload operators, it's not something that is allowed in Java, but you can absolutely write your own structures and then use square brackets as like indices, so you have pseudo arrays that are objects that you wrote, but again, Java just doesn't like that. Mm-hmm. Yeah, I just called it one of the arrays. How's everyone else doing? Any questions? Anyone stuck? I'd be happy to help. There's some good talking going on about where the top of the stack should be. Where should the top of the stack be?
End of the list, right?
End of the list, yes. Why? Why shouldn't it be at the beginning of the list? What happens if you want to remove the first element of a list, of an array list? How expensive is that? You have to move everything back over one place? That's not constant time. We want absolutely every one of these to be constant, a constant time operation. So because of this, the top of the stack has to be the end of the list, cannot be the beginning of the list. And that also allows us to use the size to determine where the top of the list is. If the size is 10, then the top of the stack is at index 9. If the size is 20, the top of the stack is at index 19. All right, we are out of time for the day. I'll have office hours for the next hour for those who want homework help. Try to finish this off between today and tomorrow. We'll go over it, I guess tomorrow we're either having a guest lecture or going over exams. But we'll go back to this eventually.